One example, a very basic example of how power functions can represent real-world things. If this is a square, then we can also draw a square with double dimensions, this edge being twice this edge. And of course, this edge being equal to this, and this edge being equal to this, and then this edge is twice this edge. So we have a square with doubled edges, and it's very obvious that that square can be covered with 4 of the original square. Okay, and I've written that down. This square with doubled edges can be covered with 4 copies of the original square. That is, by drawing this really carefully. This square is a little too small. This one seems to be a little bigger than these. But if I constructed this accurately, you would see that that's the case, and you would understand what I mean. So now, without the intervention of any formulas or anything you think you've learned, we can easily see that the area of this square is 4 times the area of this one. Whatever the area of this square, this one has 4 times the area. So now if we construct a graph of y equals area versus x equals side length, the graph is going to have the property that whenever x doubles, y has to increase by a factor of 4. So if I have, let's say, an x value here and an x value that's half that great, then whatever the y value is here, whatever the area is here, and let's put it about here, let's say that this area corresponds to this side length. Now, we don't have a scale in this graph. We don't know what the area is. This could be any old square, and then we can label the axis accordingly after setting up the graph. But let's do this kind of carefully. So here we have a point on our graph. This is the area of some square, or this is the side of some square, and this is its area. Now this is the side of the square with doubled sides, because this value of x is double this, so that the value of y is going to have to be 4 times as great. Now I made this a little bit big. That value of y is probably going to be up about here. Let's see, 1, 2, 3, 4, well, more or less in the A. But this means that we can locate a point that's maybe directly across from this one. Let's just accept my error in locating that point. We're going to have a point up here. Okay? Now, of course, if I cut this x value in half, which would put it about here, then I am going to get a square with an area of 1/4, because, of course, since this x is twice as big as this, the area here has to be 4 times as big as the area that I would get for this particular phenomenon, okay? So I can have a point here. And I could cut this in half and cut this in 1/4, but 1/4 of this is going to be so small that the width of the chalk line is going to obscure it. So I'm just going to stick with these few points. But of course we could do this with any number of points and make the graph, give the graph any extent we want. So now if I sketch a smooth curve through these points, okay, that curve is going to have what property? Well, it's going to have the property that when x doubles, y increases by a factor of 4. Well, this works out in the context of what we've done so far. This is a factor 4 graph. Y increases by factor 4 when x doubles. The factor 4 graph. We could say y quadruples when x doubles, since quadrupling is increasing by factor 4. Y changes by factor 4 when x doubles. Okay, and this represents the factor 4 power function. This is a power function, very important power function, maybe the one that occurs most frequently in the world, in nature, in physics, and in many of other things. It's one of the most common functions that we ever encounter. And it arises from this simple geometric fact about areas. Now, what if we wanted to know the area of a square if the area that we get for a square if we increased the side by 50%. That is, we change the length of the side by 150%, or 1.5. 1.5 times the length of the side. So let me actually just kind of sketch that lightly on here. A square has 50% more sides that are 50% bigger. I'm not sure how well I did that. Now we can subdivide this in various ways and figure out exactly what we would have. We could do it geometrically, but let's just say all we have is this graph. How would we figure out the area of this square as a multiple of the area of this square? In other words, by what proportion does the area of a square change if we change the length of the side by factor 1.5? So how do you think we would use the graph to do that? You might stop and think about that for a minute, but I'm going to come back in a minute and I'm going to have a few things marked on the graph. Okay, I didn't lie to you, but I changed my mind. I'm going to mark them right in front of you. Okay, let's just take this side here. Let's take this length here, and let's increase this to 150%. Now that's going to be halfway between the original length and the doubling, so it's going to be easy to locate that point. Okay, now I try to go up to the graph, and let's try to go up vertically. Easier if I do it from the bottom. So that seems to take me up here, okay? And then I project this over, hopefully at a good horizontal, and I obtain this, okay? Now, I didn't do a real good horizontal. We can see that that one's going downhill, so I'm going to kind of fix that. Okay, now I'm not sure that's perfectly parallel to the x-axis, and the x-axis kind of gets a little wobbly anyhow, but this distance here appears to be very close to the same as this distance. So I think that's probably about right. Now, my question is, okay, well, if we draw this line here to represent our original value, and this line here, then this line is 1.5 times as long as this line, indicating a side length that's 1.5 times as great. Now if I draw a little line corresponding to my original area, and then a line corresponding to my new area, what do we get? Well, let's see. This line, and we add it, it's a little more than twice as long. Okay? So the factor between these two lines is 1.5. And the factor between these two lines is a little bigger than 2. A little bigger than 2. Maybe 2.2. Now, it's pretty easy to prove in this case that if this thing is perfectly constructed, then the factor is 2.25. We can prove that algebraically, or we can prove that geometrically by cutting up the pieces of our extended square. The geometric proof is pretty immediate. You notice I've added a couple of lines here. And remember, this is supposed to be 1.5 times this, which means this is half of this. So that it would take 2 of these to make up this area. Well, that means I could put one of these inside here and another inside here. And it's very clear that they would have the same area as the original square. And then what about this little square here? Well, this little square has half the dimension of the big one, which means that we can put 4 of these inside here, just like we put 4 of these inside here. So that each of these is half the area of the square. To put them together, you get equal to the area of the square. This is 1/4 the area of the square. So you have now 2 1/4 times the area of the original square. So we get 2.25 to refine our graph estimate of 2.2. Of course, the graph estimate was made just by some ballpark estimates. We might have come up with 2.3 or 2.4, or even 2.1. But we see that the graph, if perfectly constructed, would have to tell us that this area is 2.25, rather that the ratio of the areas is 2.25, when the side factor is 1.5. Now we can even apply a little algebra here to get something even more profound. I'm going to claim that if y equals cx squared, where c just stands for some constant number, could be 2, could be 14, could be 58 acres per square meter, it could be anything, okay? If that's the case, then the value of y forples when the value of x doubles. Now, what's that have to do with the graph? Well, that's exactly what the graph does. The value of y forples when x doubles. Now, I just used the word forples, and you might not know what that means. Well, we've seen that the values of x double, and the values of y for some graphs that we've already seen triple. So what happens here? Well, doubling means you increase by factor 2. Tripling means you increase by factor 3. So what happens if you increase by factor 4? Well, you forple. Now, really that is quadruples, but we're going to say forples because it's a more striking word. Probably has all kinds of connotations for you, but all it means is the graph quadruples. So we're going to use the word forples for this graph. It's a really important graph, so we're going to give it a really special name, not quadrupling, forpling. Okay, so how do we show that this is the case? That this is a graph of y equals some constant times x squared. Okay, well, we're going to say we're going to let x2 stand for some value of x, and x1 stand for some other value of x, with the property that x2 is twice as big as x1. Okay, now we're going to then let y1 and y2 be the two corresponding y values. So you might think I'm going to write that, maybe write it yourself before I write it, and then see who has the better expression. Might as well be you. Well, I've just written this as y2 equals c times x2 squared, since y equals cx squared. y1 equals cx1 squared. These are going to be the values of y that correspond to the values x1 and x2, again with the assumption that x2 is double x1. Okay, I can say then y2 divided by y1 equals cx2 squared divided by cx1 squared. And what does that equal? How would you simplify that? You should simplify that and see what you get. Okay, one thing I would hope you would do is you would see that this is equal to x2 squared divided by x1 squared. This is not because you can cross out those c's. I don't like cancellation. It's because c is divided by c, and c divided by c is 1, and 1 multiplied by x2 squared over x1 squared is just x2 squared over x1 squared. That's a fundamental rule. Cancellation is not a rule. People would, well, never mind, see all kinds of bad cancellation, and it drives me nuts. Okay, how else could we express x2 squared over x1 squared? Okay, well, according to the laws of exponents and to all the laws of multiplying fractions and so forth for all kinds of reasons, we could write that as x2 divided by x1 quantity squared. Well, now, we've proven then, or we've almost proven that doubling x forples y. Let's see how. The one thing we haven't yet made use of is that x2 equals 2 times x1. So that, well, if x2 is 2 times x1, then what's x2 over x1 squared? What do you think? Well, I think that that equals 2x1 over x1 squared, since x2 is 2x1, which equals 2 squared times x1 squared over x1 squared. x1 squared divided by x1 squared is 1, and then the 2 squared gives us 4. Now, does this show that y quadruples when x doubles, or that y forples when x doubles? Convince yourself that it's so. So doubling x forples y, and our graph represents y equals cx squared.